we're into the second half of this chapter on ideal gas mixtures. The first half was just general ideal gas mixtures. Now it's specifically dry air and water vapor. Psychrometrics, the study of moist air. So we had the concept of dry air, and with the dry air, we know that the molar mass of dry air is what? 28.97 kilograms per kilomole. If you have water vapor in it, then you have the molar mass of the vapor is about 18.02 kilograms per kilomole. The mixture can range from being completely dry air to saturated air. So moist air is in between. And saturated air is when the partial pressure of the vapor is equal to the saturation pressure of water, straight out of the tables, at the dry bulb temperature, or the temperature of the mixture. And if it's moist air, then we know that the partial pressure of the vapor is less than Psat, and the least that PV can be, the partial pressure of vapor is 0, then it would be dry air. All right. The total mixture pressure is the combination of the dry air and the vapor pressure. There's 3 temperatures that we need to be very familiar with: the dry bulb and the wet bulb. The dry bulb is the temperature most people would associate with the normal temperature of the air. All right, the wet bulb senses how well water can evaporate in that air. And the difference between the wet bulb and the dry bulb is a measure of how dry it is. So the wet bulb temperature is less than the dry bulb temperature. If the air is completely saturated, if it's saturated air, does it have the potential to evaporate? So, no. And so guess what happens to the difference between those two temperatures when it's now 100% relative humidity, it's saturated air? There is no difference in the wet bulb and dry bulb. That sling psychrometer, you'll have 2 same temperature readings. Okay, the wet bulb is equal to the dry bulb when it's saturated air. The dew point temperature is associated with a concept of constant pressure cooling, and the partial pressure that it starts with will be the same until it can't be that high anymore, until the partial pressure of the vapor in the moist air mixture is equal to the saturation pressure at that lower conceptual dew point temperature. Think about it both conceptually. I'm just going to start cooling this moist air mixture, and when it becomes saturated air, it's ready to start to condense. That's the temperature at which I'll call the dew point temperature. And you have a lot of physical experience with dew point temperatures, both on cold containers in a hot, warm room, as well as maybe in a window pane in the winter. Hey, are we going to get a cold blast? Did you hear about the weather's changing? Watch out, we may have an early freeze this fall. It's not winter yet, is it? We're still in the fall, right? So you can have water on the inside of windows in the winter inside your house. That's condensate from the low temperature of the window pane being below the dew point temperature of the air in the room. And then you can have other great applications. Why does dew form on the grass or on your car in the morning when it's not too dry? Not every morning do you have dew on your windshield or other parts, your rooftop or in the grass, but a lot of mornings you do. So those are the 3 temperatures. There's 2 humidities. The relative humidity, phi, it's defined in terms of mole fractions, but we use it in terms of because the vapor pressure. So the vapor pressure is equal to the relative humidity times the saturation pressure. How far or how close you are, it's relative to being saturated air. So if you have dry air, it's 0% relative humidity. If you have saturated air, it's 100% relative humidity. And then the humidity ratio, omega, was defined as the mass of vapor in a moist air mixture divided by the mass of dry air in the same volume of the mixture. Sometimes we think about a fixed volume. So that's a ratio of masses for the same volume. When the dew point temperature is 25 degrees C, what percentage of the moist air is vapor? So when you think about the percentage of the moist air, what percent is vapor? Think about a volume. Maybe the volume is 1 cubic meter. Think about calculating the mass of the vapor in that cubic meter. Calculating the mass of the dry air in that cubic meter. The total mass that's in of the gas is the sum of the mass of the vapor plus the mass of the dry air. And then if you wanted to calculate this percentage of the moist air that is vapor, wouldn't it be the mass vapor divided by mass total, which is mass vapor plus mass dry air? That's all. Calculate that percentage. Note that we'll assume that the atmospheric pressure is 101.3 kilopascal. So that gives us a total room pressure. And the saturation pressure at 25 degrees C is 3.170 kilopascal. How about if I give you a minute to work with it? Stay with algebraic notation for a minute, and then if you have time, substitute numbers. Make sense? See what we're asking you to solve for? It's a mass fraction. What percent of the moist air is due to vapor? All right, so we want to calculate this ratio, this mass fraction. What is the mass of vapor that's confined to a room of volume 1 cubic meter when it has the dew point temperature of 25 degrees C? That's the first thing. Calculate the mass of vapor in 1 cubic meter. So how would you do it? You would assume it's ideal gas. You'd use ideal gas equation, something like PV is equal to mRT, right? Or R bar over the molar mass of the vapor, because we're looking to calculate the mass of the vapor. And then you'd use the same equation if you knew the partial pressure of the dry air, the volume of the room. You'd calculate the mass of the dry air using ideal gas equation, the molar mass of the dry air. So those two equations we need to use. That's all. So the mass of the vapor is going to be the partial pressure of the water vapor in the moist air mixture times the volume of the room times the molar mass of vapor divided by R bar T. And when you do that ratio, m sub v over m sub v plus m sub dry air, you'll get the P sub v molar mass of the vapor divided by P sub v molar mass of the vapor plus P sub dry air times the molar mass of dry air. Did I do the algebra correctly? Thumbs up, you agree? Right? Okay. So what is the molar masses? Those are easy. That's 18.02, and the molar mass of the dry air, 28.97, both units kilogram per kilomole. But we need to get the partial pressure of the vapor. Well, it said that the dew point temperature is 25 degrees C. Isn't the equation for the dew point temperature that the partial pressure of the vapor currently in the moist air mixture is equal to the saturation pressure at that dew point? So we look up the partial pressure. Well, it's given right here. The saturation pressure is 3.17 kilopascal. So what we find is it's 3.17 kilopascal times 18 divided by 3.17 times 18 plus 101.3 minus 3.17 times 29. All those numbers look good to you? So when we run this, we find that this is right at 2%. So the water constitutes 2%. Water vapor constitutes 2% of the mass of moist air when it has a dew point temperature of 25 degrees C. That's a lot of water vapor in the air. All right. Well, what we can do is we can vary the dew point temperature, and I know I switched it to degrees F because a lot of us think in degree F, and looked at the mass fraction of water vapor in the moist air. Just resolved that problem for a bunch of different conditions for the dew point temperature. And so if the dew point temperature is relatively low, 50 degrees F, you're down in this vicinity. For the percent of the air that you're breathing, that's water vapor. And as it goes up, around this 2% is right in this vicinity, right? About 78 degrees F. So that's the condition of 25 degrees C. 77 degrees F, 25 degrees C has a mass fraction right at 2%. And then it continues to go up, and it's rapidly increasing as the dew point temperature increases. So a lot of times you can sense how comfortable you are in the room if you know the dew point temperature, so that if it's less than around 55 degrees F, most people would say, oh, it's a pleasant condition in this room or outside. And the mass fraction of vapor is low, less than 1%. But as the amount of moisture gets up, sometimes, especially if you have elderly, you sense hard to breathe when it's thick. That's how they'll describe it. Even though the molar mass of vapor is lighter, but it interferes with getting oxygen out of the air in your lung linings because of that moisture. So they'll describe it as being comfortable, and that's getting a little sticky as that dew point temperature increases. It's uncomfortable, it's oppressive, it's miserable. Let's solve this problem. It says, show that the humidity ratio can be expressed as omega is 0.622 PV over P minus PV. What are each of the terms here? Well, that's the humidity ratio, but what is PV? Partial pressure of the vapor. The partial pressure of the vapor can vary between 0 and the maximum, the saturation pressure at that temperature. What is P? P is the what? It's the mixture pressure. It's the total moist air pressure. So P is equal to the PV plus pressure of dry air. True? So right in the denominator, they have P minus PV. Well, guess what that is? That's the partial pressure of the dry air. That's what that is. So let's start and say, well, remind me, what is the definition of humidity ratio? Is it the mass of vapor per mass of dry air? Sure. Let's consider a uniform, the same volume. So this volume is the same as that volume. I think it's a lot of times easy to think of mass in a cubic meter. Mass of vapor in a cubic meter, mass of dry air in a cubic meter. Well, this is rho of the vapor, isn't it? What's rho? Mass density. And this is rho of the dry air, the mass density of the dry air in the same volume. So can I use the ideal gas equation for both the vapor and the dry air? Sure, they behave as ideal gases. And so the equation is P is equal to rho R bar T divided by whatever molar mass you have. So rho for the vapor is going to be the partial pressure of the vapor, the molar mass of the vapor, divided by the universal gas constant and the dry bulb temperature. Likewise, rho of the dry air, the partial pressure of the dry air, the molar mass of the dry air, divided by R bar T. We cancel the R bars and the T's, and we're left with this expression. So the molar mass of vapor divided by the molar mass of dry air times the partial pressure of the vapor divided by the partial pressure of the dry air. So far, this is the same, right? So it must be true that the ratio of those molar masses is equal to 0.622, and they are. So the molar mass of vapor, which is 18.02, divided by the molar mass of dry air, which is 28.97, gives you that constant 0.622. A lot of books put the 0.622, and they really don't, well, they may explain why it's equal to 0.622, but I think a lot of people out there in practice, they forget, oh, that's just the ratio of molar masses. But that's all it is. So this is a very quick way of calculating omega, the humidity ratio. Justify the assumption that water vapor in saturated air at 30 degrees C behaves as an ideal gas. How do we justify an assumption that something behaves as an ideal gas? Forget it's water vapor. How did we justify that carbon dioxide at this pressure and temperature could be treated as an ideal gas? Your prior knowledge. How would you have done that? Justify that, some mixture, sulfur hexafluoride, something, is an ideal gas at this temperature and pressure. How would you do that? You would think of the compressibility factor. And so we recall that you would have a modified ideal gas equation. PV is equal to Z RT, or let me put it this way. Let me put it like this. PV is equal to Z RT. There you go. And what is Z is a compressibility factor, Z, which says that you have the pressure, then you have the specific volume divided by RT. And if that's close to 1, then we say we have justified the use of the ideal gas equation. Then we would throw out the Z, and you would just have PV is equal to RT. Typically, it's not spot on 1. It's 1.00 something, but it's close enough to 1, right? Well, think about taking this and just adding a subscript IG to this V. What does that mean? That's the specific volume, assuming it behaves as an ideal gas. So I could take this group of terms and replace it by the actual specific volume divided by the ideal gas predicted specific volume. Sometimes the compressibility factor's described as a ratio of specific volumes. Make sense? So let's do this. What is the actual specific volume for water vapor in saturated air at 30 degrees C? Experimentally, out of the table, somewhere, get that value, and then compare it to the specific volume of the ideal gas, of the vapor, assuming it behaves as an ideal gas, and calculate it by the equation RT divided by P. So how am I going to get this one? Out of the tables. So how do you get the specific volume of saturated vapor? Water vapor, it's in saturated air at 30 degrees C. What is that? V sub F or V sub G? V sub G at 30 degrees C. True? And then the other, let's go ahead and report that value. 32.894 meters cubed per kilogram. So what we'll do is now compute the specific volume assuming ideal gas behavior. Its R is 8.314 divided by the molar mass, 18.02. We had a temperature of 30 degrees C. We convert that to 303 Kelvin. And you divide by the pressure. Well, this is the partial pressure of the vapor in the mixture. That's the saturation pressure. That's equal to 4.246 kilopascal. So when we compute it, we find it's 32.92 meters cubed per kilogram. And now we do the comparison. Are they reasonably the same number? Sure. And so what we find is that V sub G minus V sub IG divided by V sub G, the absolute value, is less than 0.1% difference. So the difference between the two specific volumes is less than 0.1%. That's spot on, right? So that's how you justify treating the water vapor as an ideal gas. Did we solve this problem? I know I solved a similar problem. Let's go through it then. A room contains air at 29 degrees C, 97 kilopascal. The partial pressure of the water vapor is given. So we know the temperature dry bulb, 29 degrees C. The total pressure, 97 kilopascal. And the vapor pressure is 3.364 kPa. Determine the partial pressure of the dry air. How do we calculate the partial pressure of the dry air? It's P minus PV, right? So the partial pressure of the dry air comes right in at 93.64 kilopascal. Answer to part A. Now about part B. What's the relative humidity? PV over Psat. And it's a sat at the 29 degrees C. So our current pressure, 3.364 divided by 4.247 gives us a relative humidity of 83.9%. What's the dew point temperature? That's where you have the actual vapor pressure is equal to the saturation pressure at the lower temperature. That lower temperature is called the dew point temperature. So we know that this is 3.364 kPa. So I want to find at what temperature, the dew point temperature, is the saturation pressure equal to 3.369 kPa. And we just look down in our table and we look at 3.364. Did I say 39? Well, anyway, that's the same number, right? So the dew point temperature, 26 degrees C. Can the dew point temperature be greater than the dry bulb temperature? No. It's always less. Can the dew point temperature equal the dry bulb temperature? When it's saturated air. What is the mass of the water vapor in a volume of 1 cubic meter? So we want to calculate that mass of the vapor. If we use the ideal gas equation, maybe use this form of it. PV is equal to M R bar T divided by the molar mass. And we're interested in the vapor mass of the vapor. So we use the molar mass of the vapor and the partial pressure of the vapor in the moist air mixture. Okay, so the mass of the vapor is equal to the partial pressure of the vapor, the volume of 1 cubic meter, the molar mass of vapor, 18.02, divided by universal gas constant, and the absolute temperature. This chapter is just ideal gas equation again and again and again, right? All right, so we calculate the mass of vapor in 1 cubic meter to be 0.0241 kilograms. Sometimes I'll emphasize that's vapor, kilogram of vapor. Because within that 1 cubic meter, you also have so many kilograms of dry air. What is the humidity ratio? Well, omega That's the mass of vapor per mass of dry air. We worked it out to be 0.622 times pressure of vapor divided by pressure of dry air. So we know the pressure of the vapor, the pressure of the dry air, the ratio of molar mass is 0.622. Calculate the humidity ratio, 0.02235. And again, it's kilogram per kilogram, so it's truly dimensionless. But it's kilogram of this type, it's kilogram of vapor per kilogram of dry air. So a lot of times I'll add that as units, but really you could leave it dimensionless. It is dimensionless. Dimensionless, or you can put kilogram vapor or kilogram dry air. Either way, I'm not going to take off points for that. All right? Anybody else a comment or a question? Let's talk about air and water balances, and I'm going to talk about heating application and a cooling application. So you have a duct, and you're bringing in air at state 1, and you're taking it out at state 2. And you have a coil, and inside that coil runs a hot fluid. A lot of times it's water inside a coil. Sometimes it could be different type of fluid, a refrigerant. It could be, I don't know, Dowtherm or some other fluid that has some glycol in it. It's heavy. It's not really water anymore, but it won't freeze if you get it really cold. Okay, but it has good thermal properties. Another application is a cooling. So I have another coil and some fluid running through it. Could be refrigerant, could be water, could be other liquids. And you bring in air at state 1 and pass it over that cooling coil, and you take air out at state 2. True. So when we look at our what's happening here, you better have a tray underneath one of these coils to collect some liquid. Do I need it under the heating coil, or do I need the tray underneath the cooling coil? I need a tray underneath the cooling coil such that it can collect up and handle the condensate. The water that's going to be taken out of the moist air flowing over a cool coil. The cold coil could be below the dew point temperature of the inlet air. If the surface of the cold coil is below the dew point temperature of the inlet air, I'll have condensate form on it. It'll drip off, collect into a pan, and there you go. So this is a condensate coming out. Do I need a tray underneath the heating coil? No, you won't. Because if you're heating up the air, it can handle more moisture. All right. So first of all, we'll introduce a little control volume. So it's coming in at state 1, leaving at state 2. And we'll do first of all an air balance. So the mass flow rate of dry air entering state 1, that's the only source into the control volume of dry air. It's equal to the mass flow rate of dry air leaving at state 2. That's the only way it's going out of the control volume. It's running at steady state. Is there any more in or out source or sink of dry air for this problem, or is that a good air balance? We're done with the air balance. And so a lot of times they look at that and they say, well, this is pretty trivial. They just say m dot dry air is equal to a constant. It's the same in is equal to the same out. Do the same on the cooling side. M dot dry air is equal to a constant. Now let's do the water balance. Now we move to the water balance. What do I have for a source of water flowing into that control volume? Some water vapors coming with the inlet state 1, isn't it? Could I write it as omega 1, mass of vapor per mass of dry air, times the mass flow rate of dry air? That's the in, right? Do I have any other ins? No. And all I have is an out, omega 2 m dot dA going out. What do I conclude about the single inlet, single outlet airflow over a heating coil? These cancel. Omega, humidity ratio is the same. Does that mean the relative humidity going out is the same as the relative humidity coming in? No. I heated up the air. The temperature at 2 is greater than the temperature at 1. It has the capacity to hold more water vapor in it. Hot air can hold a lot of water. Okay? So this is not true. But this is true. Omega is equal to omega. 1 is equal to omega 2. Make sense? All right, let's do it now for the cooling application. So any source of water in, let's just do all the water in is equal to all the outs, the sum over the outs. So we're going to have omega 1 m dot dry air. Any other source coming in? No. Going out, we're going to have omega 2 m dot dry air plus the mass flow rate of the liquid condensate leaving, m dot LIQ. I don't have a better symbol than that for that term, but it's the mass flow rate of the liquid condensate leaving. Well, we use this equation to calculate how much liquid leaves. It's equal to the mass flow rate of dry air times the change in the humidity ratio. Comes in large, high humidity ratio, leaves a lower humidity ratio. So moist air at 25 C, 100 kilopascal, and 75% relative humidity flows over a cooling coil with a dry air flow rate of 2.5 kilograms per second. So the mass flow rate of dry air is 2.5 kilograms per second. And you flow over a cooling coil. And it comes in at state 1, exits state 2. The temperature 1 is 25 degrees C. The pressure is always 100 kPa. So that's the total pressure. Okay, maybe put that right here. It's 100 kPa. And relative humidity is 75%. The air leaves at a lower temperature, 12 degrees C, and phi2 of 95%. Let's take a look at these numbers. Does it make sense that it cooled from 25 to 12 degrees C? Does it also make sense that the relative humidity went up from 75% to 95%, or is that a typo? Is that impossible? Because it's so much cooler, it cannot hold as much water. So the relative humidity normally on cold air is modestly or pretty high. If you really want to be miserable in the winter, right, have very dry cold air. But by itself, cold air is usually pretty dry anyway. Okay. So there you go. Those numbers all make sense. Determine the volumetric flow rate of air entering the coil. So that's the AV coming in. That's going to be the product of the mass flow rate of dry air times the specific volume of dry air entering. True? Use the ideal gas equation for the specific volume of dry air entering. R bar T divided by the partial pressure of the dry air times the molar mass of dry air. And to get the partial pressure of the dry air, we need to subtract off the current vapor pressure. And the vapor pressure is equal to the relative humidity times the saturation pressure coming in. It comes in at 25 degrees C. So the saturation pressure at 25 degrees C. Let me find my numbers here. Saturation pressure at 25 degrees C is 3.17 kilopascal. So the vapor pressure coming in, 2.377 kilopascal. So the dry air partial pressure, 97.623 kilopascal. The specific volume of dry air, 0.8760 meters cubed per kilogram of the dry air. And you calculate the volumetric flow rate, AV, coming in to be 2.19 meter cubed per second, which is also 131 meter cubed per minute. So there's the volumetric flow rate in. That's the answer to part A, okay? All right. How about condensate flow rate leaving the coil? You have to have a little pan, and you have the mass flow rate of the liquid condensate leaving. You do a water balance. From the water balance, you have that the mass flow rate of dry air times the inlet humidity ratio minus the exit humidity ratio is equal to the mass flow rate of the liquid condensate leaving. So we need to calculate omega 1, 0.622, pressure vapor 1 divided by pressure dry air 1. We calculate it's 0.01515 dimensionless, or kilogram vapor per kilogram of dry air. Omega 2, similar equation, similar work. You calculate it's 0.00840. Compare the two numbers. Omega 2 is less. There's been some dehumidification. And you calculate the mass flow rate of the liquid to be 0.0169 kilograms per second, or 1.01 kilograms of water per minute. All right. Does that look good?